Okay, so welcome to the fourth course, for the fourth lesson. Today we are going to focus on a very particular, very interesting phenomena, the one that we already mentioned. We are going to speak about the electrifying brain like the third lesson, but in this case we are going to talk about the active signal, the spike. We already saw spikes. The spike is an all or none phenomena, a 0-1 phenomena. We shall try to understand today why is it all or none phenomena. And as we mentioned, the spike appears in axons. And as a consequence of the spike in the synapse, we will see in the postsynaptic part the synaptic potential. So here are the two types of potentials in the nervous system. The action potential in the axon, the synaptic potential in the dendrites. And we mentioned in the last course, in the last lesson, that this synaptic potential has two types, excitatory and inhibitory. But today we are going to focus on the spike, which is a very interesting, unique phenomena to the nervous system. We'll start with axons as excitable tissues. When I say excitable, I mean a tissue that generates spikes, generate a very nonlinear, highly nonlinear phenomena that we shall discuss at length. Then we'll discuss the Hodgkin-Huxley experiments. So Hodgkin-Huxley are the heroes of the spikes. We shall discuss a lot Hodgkin-Huxley. These were two giants, really two giants. And we shall discuss their concepts, the techniques, the experiments, and eventually the model of Hodgkin-Huxley. We'll discuss the voltage clamp and the space clamp, the voltage clamp and the space clamp technique that they developed that enabled us to really understand the spike. We'll speak about the conductances and the currents underlying the spike. So the spike is a membrane phenomena. It's current flowing through the membrane. It's conductance changes that are voltage dependent, and we'll discuss that. So the conductances underlying the spike. And then we'll end with the Hodgkin-Huxley model, the mathematics of Hodgkin-Huxley, that I can say, and I think most people will agree, that after having the Hodgkin-Huxley equations, we understand the spike. We'll eventually end by showing that the spike not only is generated locally in the axon, but as we already mentioned in the second lesson, the spike propagates along the axon. And then I want to summarize this lesson by showing how synaptic inputs are transformed into spikes in a single neuron. So a single neuron carries two signals, synaptic potentials in dendrites and spikes in the axon, and the synaptic potential generate the spike. Okay, so let's continue with these two giants. So here you see Sir Alan Hodgkin. Here you see Sir Andrew Huxley, both working in Cambridge, actually before the war, the Second World War. And these two people really are identified with a spike, or what they call the action potential. And they got for this absolutely amazing work the Nobel Prize in 1963. And they used, and this is one of the magic of deciding on which preparation is the right one to choose, to select, in order to get an answer to a question. They selected the squid. This is the squid, an animal that is not doing very much but is alive, knows to escape very well whenever you hit it can go fast. And this animal, the squid, has a very special thing. It has a giant axon, a very wide, a very thick axon. So here you see the squid giant axon. This is from the original work of Hodgkin and Huxley, and also of Katz, already from 1939. They succeeded to do something absolutely fantastic. They took the axon, so you see here a piece of an axon here. This is an axon, only a part of the axon. This is a very thick axon. So unlike the axons in our brain that are very thin, on the order of micrometer, a thousandth of a millimeter, here you see an axon that is very thick. It's about half a millimeter, 500 micrometer, a very thick axon. And this axon, because it is so thick, it enabled Hodgkin-Huxley to penetrate axially through the axon with a wire, with an electrode inside. You can think about this like a toothpaste, where you can put into the toothpaste an axial wire, an axial core. So you see really the original axon of the squid with a core, with an electrode, axial electrode. And this is only because it's so thick. We cannot do it in thin axons even today. We can penetrate with an electrode to thin axons, but we cannot do axial electrode in real axons. And so here you see the first spike ever recorded intracellularly using this technique. So you see in 39, Hodgkin and Huxley, as I said, penetrated into an axon, into the squid giant axon. They penetrated with an axial electrode, and using this electrode and electrically stimulating the axon, they saw this beautiful all or none phenomena. We shall talk about all or none in a second. So here you see a recorded spike on the oscilloscope of Hodgkin-Huxley in 39. It was the first ever intracellular direct recording of a spike. So let's speak about this spike for a second. This is voltage here. So you see the spike starts from the resting potential. And if the stimulus here is strong enough in a depolarizing direction, and that's very important to remember, if the stimulus here is strong enough, they gave current stimulus here to the axon, suddenly you see this boom, this firing of a spike. We call it firing of the spike. So the spike suddenly, the voltage suddenly changes, goes up, depolarizing, and then go down even below the resting potential, and with time goes back to resting potential. You can look at it also using a white background, so it's the same recording actually. So you see the electrode, you see the axon, and you see the stimulation here, and suddenly here, if there is enough depolarization, boom, you see the spike. And this is about millisecond long. So this is the spike. This is a new phenomena. People knew about this phenomena, but they never saw it in such fine details. So let me say a few words about the spike. Again, it starts from the resting potential. It requires a stimulus, in this case current stimulus, and you know that in real cells we don't get current stimulus from electrodes, but rather stimulus from synapses. But here there is a current stimulus into the axon, a depolarizing current stimulus, and if this depolarizing current stimulus is strong enough, you get this upstroke of the spike. This spike starts from minus 60 or minus 50, goes up, 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 cross the zero, becomes even more positive inside than outside. Remember, the resting potential is more negative inside than outside, and suddenly the spike reverses. For a brief period of time, the inside of the axon becomes more positive than the outside, and then the spike ends itself, finishes, repolarize back into the resting potential, even below the resting potential. So this is called after hyperpolarization. After hyperpolarization, this is called overshoot. So you overshoot above zero, you undershoot below the resting potential, and if you wait a few milliseconds, the spike disappears. So this is a transient phenomena, a very brief phenomena, on the order of a millisecond or less, depending on temperature. In this case, it was done in a cold temperature, 6.3 centigrades. This is where the squid likes to live, in cold sea. And so this is the phenomena which is really in all its glory is shown for the first time ever. So the mission of Hodgkin-Huxley was really to try not only to record it, which is beautiful, to show it, and to really analyze the upstroke and the downstroke, the overshoot and the undershoot, the after hyperpolarization, but try to understand the membrane mechanism that enables this phenomena to occur. You understand that this phenomena, and I mentioned it already before, is a general universal phenomena for all nerve cells, or almost all nerve cells generate this spike. So it's a universal patent of neurons to carry information, to generate electrical signals that signify, that represent information, outside information, visual, auditory, or internal information, depression, feelings, creativity, and so forth. It's a very, very, very important signal that nerve cells know how to generate. And the question of Hodgkin-Huxley was, what are the membrane mechanisms in the axon that enables this fantastic phenomena, all or none phenomena? So I need to show you that it's an all or none, meaning that if the stimulus was not strong enough, there would not be an action potential. And what they did eventually, and I will come to it at the end, Hodgkin and Huxley, after recording it, worked for several years and came with a set of absolutely beautiful set of papers for which they got the Nobel Prize. And they eventually end up with 4 ordinary differential equations. 1, 2, 3, and 4. 1, 2, and 3, and 4. These 4 equations, the Hodgkin-Huxley equations, capture the essence of the action potential. If you solve this equation, and we'll discuss this equation, so this is not going to be a very simple lesson, but I'll try to make it as simple as possible. If you solve this equation for V, for voltage, you will get the solution will behave like an action potential. So I can say that after writing these equations in 1952, we understand the action potential in a very compact, in a very systematic way. I see it as a triumph of theory. Actually, I don't think that today we have such a beautiful theory in neuroscience as the Hodgkin-Huxley theory for the spike. So my role today is really to try to understand, to explain to you how did Hodgkin-Huxley came to write these equations step by step, connected to experiments. So each of the parameters here derives from experiments. And eventually they succeeded to write these equations that, as I will show you at the end, really replicate, the equation replicate the action potential, but also predicts new things that were not part of the measurements or direct measurements of Hodgkin-Huxley. So this is really the role of this lesson, to tell you, to go with you through the process of Hodgkin-Huxley, starting from the experiment, recording the action potential, then develop techniques to decipher each of these parameters, and eventually, compactly, with 4 equations, capture the action potential mathematically, meaning understanding the action potential.